Hi, my name is Sergio. I'm a graduate student at UTEP. I will present the work that I did for the class Computational Mechanics. So this work is based on a model survey and random vibration analysis of a CubeSat. So this is the outline of this video. First, I will go in the background, then the motivation, the objectives, geometry, boundary conditions, materials, mesh optimization, simulations, conclusions, and what could be done for future work on this project. Some background: CubeSats have been able to provide affordable access to space for universities and research. The dimensions and weight of a CubeSat are standardized. So usually for a 1 unit CubeSat is a 10 by 10 by 11 centimeters, and the weight is 1.33 kilograms. However, many configurations are used. So for example, this figure shows a 3-unit configuration, which is just a 1-unit CubeSat stock. All this information can be obtained in this website of NASA. CubeSats need to be built of space qualified materials. So and also they must undergo several test requirements. Some of them I did not list all of them, but they include structural and mechanical verification, vacuum, thermal, and humidity requirements, and generalized random vibration testing. So an example of, for example, a qualified material needs to meet the humidity standard or a strength standard. I got this information from the environmental verification standard from NASA, and this is for flight programs. So in this figure, I show some of this testing, and I got this from the paper that is listed on the bottom of this slide by Ampas Sokolo et al. So in the top figure, it shows the results from a random vibration test on FEA, and in the bottom figure, it shows thermal testing. The main motivation of this project is to design a CubeSat that is capable of changing direction, meaning that it will have thruster, that it can record data, for example, video recording, or it can take pictures, and that it can transmit that data back to Earth. Also, it will be capable of generating energy with a photovoltaic panel, for example, and is capable of storing that energy. So I researched several CubeSat components. So again, to meet the motivation objective, the CubeSat needs to be able to change direction. So I included a thruster. I selected this one because it meets the dimension requirements, and it has a relatively low mass of 640 grams empty and 870 grams with the propellant. And also it requires a supply voltage of 12 volts. So to supply the voltage, I selected batteries. So this one has a mass of 180 grams per unit, and it supplies 3.7 volts per unit. Also a computer, a photovoltaic panel, a camera, and a transmitter to transmit the data back to Earth. As you can see on this plot, the mass of the components that were presented in the previous slide. So the total mass came out to 2.4 kilograms, which only leaves 270 grams for the frame of the CubeSat. Also, it was obvious that a 1-unit CubeSat is not enough for these components in terms of mass and volume. So I decided to use a tube CubeSat geometry for this project. The main objective is to validate a 2-unit CubeSat for flight and to keep the mass below 2.67 kilograms, including all the components that I listed previously. And for this, I divided the research objectives in 3. First, a model survey, then a random vibration simulation according to NASA standards, and then optimization of the structure to meet the weight requirements. However, I found that this is an iterative process, so I basically jump between these 3 objectives. So the geometry must fit on the Cal Poly orbital deployer, which is this. So it needs to have the CubeSat needs to have rails to be able to slide here, and so this deployer has a spring that pushes the CubeSat when it's in space. Also, the CubeSat have spring separators as well. Because I decided to go with a 2-unit CubeSat. This figure shows the dimension. So for the length is 227 millimeters. Again, the other dimension is 10 by 10 centimeters. The rail needs to be 8.5 by 8.5 millimeters. And also there are some other dimension requirements that were met. All of these can be found in the design specifications by Cal Poly. So for the frame, I decided to go with the two cross sections. So first I created a line frame, and then I imposed cross sections. So for the rails, I went with squares because it needs to meet the deployer requirements, which is 8 by 8 squared. However, I tested different thickness for a hollow squared. And for the supports, which are displayed plates, I decided to go with the I structure. So it basically has a thickness, and also the height is 8.5 millimeters. So it's the same size as the squared. And all the components will be attached on the supports. So for the structural panels, I decided to create surfaces, and these surfaces cover the whole frame, as you can see on the top figure on this one. On the bottom figure, you can see where the components are where they go. So the thruster is here, and this is I basically created this CAD from the dimensions specified by the manufacturer. So the battery goes here, then the camera here, and the computer. The photovoltaic panels will be attached on the outside. So on this slide, I show the boundary conditions that I used. I basically used a pre-stressed boundary condition and a non-pre-stressed boundary condition. So for the first one, I used the forces specified by Cal Poly on the deployer. So basically, it's the force that the pin applies into the CubeSat. Also, I created a displacement condition on the rails, fixing X and C. Also, basically X runs here, and then C and Y. So I fixed C and Y to 0, and then I left free X, and then I created a fixed support here and here, here and here. And for the non-free stress, I just replace the force by fixed supports on this vertex. The random vibration regime was selected according to NASA standards. So it's shown in the plot, or this was copied from the standard that is listed on the bottom. On the x-axis, it shows the frequency range. On the y-axis, it shows the acceleration and spectral density, which is a measurement of the vibration intensity. And it shows 4 curves, which so you can see that the ASD decreases with increasing mass. And there is a formula in the document that you can calculate what is the regime that you need for the specified mass. However, for masses of 20.7 kilograms or less, you just need to use the highest one, which is this. So this is how the data is input on ANSYS. So you can see the first step is at 20 Hz and 0.026, and then 50 Hz to 0.16 G squared Hz, and then it's flat up to 100 and 0.16, and then it goes down again at 2000 Hz. So CubeSats regard flight-proven materials. So for the frame, I selected aluminum 7075, and the relevant properties are shown here. For the structural panels, I selected a carbon unidirectional composite that is also flight proven. So this was not already on ANSYS database, so I needed to create one. So for this, I use a orthotropic elasticity model, and I just input this data into ANSYS, right? And I show what I did here. However, I want to point out that I created 3 versions of these. So for example, you see that E11 is 181 gigapascals, which is here, right? However, this is based on global coordinates. So for example, for some panels, sometimes the fibers will be normal to the panel face, which is obviously not realistic. So for this, I needed to create 3 more of these, and the 1 was changed, for example, for the y direction. Equally for the shear modulus and Poisson ratio was changed. Also, I could not find the Poisson ratio for YC, so I just assumed 0.4, which is usual for other carbon composites. So for the elements, I use bar elements for the frame that is shown here, and then for the panels, I use quad 4. However, ANSYS was not able to use quad 4. Some 3 elements were also generated. Although it was a small quantity, but just to point out. So the optimized mesh that I found was with 2.5 millimeter elements, and this led to 1549 nodes and a max skewness of 0.49. So for mesh optimization, I decided to go with the model survey as the main parameter, because the first mode is a good indicator of structure stiffness. So I plotted the model survey versus the number of nodes. Interestingly, you can see that there is some sort of sinusoidal function, and it correlates with the maximum skewedness, which is plotted here. This is the axis for skewedness, and it's shown in red. here, and so you can see on the bottom is the first mode, and then it goes to the second mode, third, fourth, fifth, sixth. After 15,000 nodes, you can see that there is not much variation. Even although the max changes, it doesn't affect that much. So I decided to go to 2.5 elements, as it was stated before. So I did not find any difference between the pre-stress model survey and the non-stress model survey. However, this was expected because the force is extremely low. So you can see the results here. So there is no difference between the in the first mode. So in these figures, I show a visualization of the first three modes that occur at 530, 547, and 553 hertz. Also, I increased the number of modes to account for the whole range of the random vibration test, meaning that it should go up to 2000 hertz. However, in the NASA document, it specified that all modes above 70 hertz can be ignored unless it's specified by the launcher. However, I decided to include them. So then I started with the optimization. So first I optimized the rail cross section. So I started with a field square, and then I varied the thickness. And for this I used the first mode. So you can see here's what with a 0.25 millimeters of wall thickness, and this is for full square. So what is important here is that the variation is too small, so it doesn't matter, at least for the simulation, what is the structure of the, or what is the cross section of the rails. However, I believe this is because of how the boundary conditions are set. I also optimized the cross section of the supports, and for this I varied the thickness of the cross section. I did not change the height because I wanted it to be the same as the rail. And again, I used the first mode for this, and you can see the thickness of the wall here and the first mode frequency. So you can see that after 1 millimeter of thickness, there is basically no change. The same for the structure panels. So again, I use the first mode, and after 1 millimeter, there was basically no change on the first mode. So for the final geometry, I decided to go with a cross-section thickness of 1 millimeter for the rail. For the support, the same, 1 millimeter, and for the panel thickness, 1 millimeter. With this, the total mass came out to 2,540 grams, which is below the 2.67 kilograms requirement. So for the random vibration simulation, I applied the regimes in two directions, first on the y-axis and then on the z-axis. So in this slide, you can see the result for y-axis. So this first contour is the deformation on the x-axis, and the maximum deformation occurred on this panel, and it came out to 0.045 millimeters. For the deformation on the y-axis, which is the same as the z-axis, the maximum deformation occurred on the lateral planner here, and it's about 0.14 millimeters, which is also the location for the highest equivalent stress, which is 17.9 megapascals, and it's here, which is much lower than the carbon composite tensile strength, which is around 3.5 gigapascals. So the second regime was applied on the z-axis, and we can see that the deformation on the x direction was also shown on the front and also on the back panel, and it came out to 0.07 millimeters. And the maximum deformation on the y-axis came out to be 0.045 millimeters. It was the same for the z-axis. However, the maximum stress in this case was found on the top and bottom panels, and it came out to be 14.8 megapascals here. I want to point out that the z-axis in this case was in this direction, and the y-axis was normal to this plane, which makes sense in this case. So it's y, sorry, which makes sense in this case because you have the maximum stress here, which corresponds to the regime on the z-axis. And also on the previous slide, we showed that the maximum stress was under the lateral plane, which corresponds to the y-axis. So in conclusion, with the simulation, I was able to design a CubeSat to endure takeoff vibration while meeting the volume and mass requirements. So these objectives were met by conducting a model survey, optimization, and a random vibration test. So for the future, the components can be included on the simulation. I tried this, but it was difficult to attach non-rigid bodies to the frame. So it basically was not allowed for model vibration or model survey, and also for random vibration.